Okay, welcome to the next video. In this video, we're actually going to walk through the process of creating some data that we're going to use to study this principal component analysis. So let's jump in. So this is going to be a toy example for studying PCA so that we know what the data is, so that we know how it's going to behave. We can have an expectation of what it's going to do. And what we're going to work with is this notion of an ideal spring. So here we've got some spring that we're looking at, got a mass on the end of a spring, starting at maybe some position x0, and its position as a function of time would be x of t. And then its velocity as a function of time would be x dot of t. And this is, if you're not familiar with this dot notation, this is a common physics notation. What this means is the first derivative of position is velocity. The first derivative of position is velocity. The second derivative of position is acceleration. This is all physics, classical mechanics. If you're not familiar with it, just bear with me, and there is some, there will be some useful math in here for you if the physics is a little bit too much. But let's jump in. So the standard model for looking at the mass on the end of the spring is to use this formula Hooke's law. The force is a function of the position, and that makes sense. There's an intuition to that. The force on a mass on the end of a spring is going to vary based on where the mass is in relation to the spring. If you squeeze the mass towards the fixed position of the spring, there will be force exerted outward, pushing the mass back. And if you pull the mass away, there will be a force pulling it back. And that's what's sort of interesting about a spring. It's going to oscillate around some static position. And then, every spring has its own K, its own spring constant. But we're not going to, we're just going to go with some arbitrary K. And then, the standard Newton's second law of physics is that the force is equal to the mass times the acceleration. So we can take these two and we can say that the force is this spring constant times the position, and that's going to be equal to the mass times the acceleration. And we can do some fancy differential equations solving to come up with this guy right here, where the position is going to be equal to the position of the spring as a function of time is going to be equal to the initial position times a cosine and the initial velocity times a sine. And if that's too much, you're just going to have to trust me. And then the spring constant is going to be baked into this omega right here, where we have the spring constant divided by the mass is this omega inside these cosines and sines. So, and you know what? Like, don't get too caught up in the math here. The point is that we have a mass on the end of a spring, and think about pulling that mass out and releasing it. You've got the mass on the end of a spring, and you pull it out and release it. And if you think about it, it's just going to oscillate back and forth. So there's an intuition to this. So let's just keep going. We're going to keep going. So this equation is going to be the true function. Now, in terms of how this relates to modeling and statistics, you think about the true function is what we're always after. We want to know what's actually happening in reality. And it's something that we could never know. We can never know the true function. But in the case here with this physics problem that's pretty clearly defined, and there's no friction, there's no air resistance, there's nothing going on, we can know this true function. So let's go ahead and plot this true function. We've got it right here. We've got the true function. We set an arbitrary omega. We say the initial velocity is 0, and the initial position is -2. So I pull the spring to -2. And we can imagine pulling the spring to -2 and then plotting, generating a vector of x values from a vector of time values, and then plotting those. And this is going to be the motion of that spring in a vacuum. So I pull it to -2 here and let it go, and it moves in time. It moves, this way, and then it comes back. And if there's no friction and no air resistance, that's what it's going to do forever. And what's weird about this plot is we've got time going in this direction. That's probably something you're not used to, but that's all right. So we've got this mass on the end of the string as a function of time. Now, in reality, there's going to be friction. There's going to be air resistance. There's going to be things that we can't control for and things that we really can't even know about, and maybe if we knew about them, there would be some other things we wouldn't know about. There's always going to be something we can't control, and we're just going to call this environmental noise. And I'm just going to add it to the function. I'm just going to add some arbitrary noise to the function. So now it's going to look a little bit ugly, right? It doesn't look so pretty. We've added some noise into the situation, and you can imagine maybe it slows down in some ways at the end of the spring, or maybe it bunches up here, or maybe it gets all clumped up here and here, and it's just noise that exists in this system that we're describing. All right, so you could imagine now this mass on the end of a spring is oscillating in our physics lab, our imaginary physics lab here, and we want to study the way that this mass is moving. So we take 3 cameras and we point them at the mass. And so, you could imagine there's an axis along the camera here pointing this way, an axis pointing that way, and an axis pointing that way. And, we pretend we don't even really know what's going on. We don't know that there's a best axis that we can put here. We just arbitrarily point 3 cameras in the direction of the mass. So we're going to be making use, one thing that's good to know is that the cosine and the sine functions are going to be working with radians, and it might be easier for us to work with degrees. That's something we might be more used to, especially because we're going to want to rotate these cameras in order to simulate having them point in different directions. We're going to want to rotate the cameras, and it's probably easier for you to understand what a 45-degree rotation in a camera is versus a pi/4 rotation in a camera. So we're actually going to convert our degrees to radians using this function right here. And actually, I think it probably should be named rads to degrees, but that's fine. We're going to keep going. So we are going to use np.pi, which is just built in for us, and we're going to go ahead and convert these guys right here. And we're going to define some rotation. So this is going to be a rotation we're going to apply to the camera. So we're going to take in a component for each measured value, and we're going to rotate it by some angle and generate an x-axis and a y-y from that. So I'm taking camera A, and I'm putting camera A at a 23-degree angle to the mass on the end of the spring, camera B at a -15, and camera C at a 65-degree angle to the mass on the end of a spring. And you can see that if the blue is the actual movement of the mass, the red is camera C, the orange is camera A, and the green is camera B. So the cameras themselves are already a little bit confused. They think that this spring is moving differently than it actually is, and this is just part of how the camera was placed. But it's important to remember that they're all measuring the same thing. They're just measuring it from their perspective, and each of them has a different perspective. So the actual thing they're measuring is the blue, but this is what they think it looks like. The red is what camera C thinks it looks like. The green is what camera B thinks it looks like, and the orange is what camera A thinks it looks like. Now there's one last kind of noise I'm going to introduce here. There was environmental noise that causes it to wobble. There was friction and air resistance and those sorts of things. But what if our cameras aren't perfect? So I'm going to introduce some noise associated with each camera. So, and not only that, the cameras could be imperfect in different ways. So maybe camera A is our best camera. It's got a 0.4 noise factor. But camera B is really bad. It's got a 1.1. And camera C is closer to camera A. So all of our cameras aren't even that good. And we're seeing how I'm creating the data right here, but you could imagine in reality, you might not even know at the beginning of an experiment which of your cameras were good and which were not so good. So here I'm going to add the noise factor in. And then I'm going to add the noise associated with each camera to the camera A, camera B, camera C data. We've got that. And let's go ahead and plot those guys. And here we go. And you can see now we've got a little bit of a problem here. We do have, you probably can use your human intuition to see that there is this linear relationship here, and there's a linear relationship there, and there's a linear relationship there. But there's clearly some issue. Camera B is clearly pretty noisy in the way it's collecting data. Camera A, camera C, they're all noisy in the way they're collecting data, and they're all looking at it from a different perspective. Now remember, they're all measuring the same original thing, but they've just done it in this way. The data that we're going to be working with is this noisy data. This is the data we're going to have. And what we want to get is this.